Beginning, I want to give us a kind of the general introduction about what we know from observations of this Arctic sea ice during the last 40 years and how much the decline can be related to climate change. Then I will talk a bit about sources, why we can predict sea ice, but also some limitations. And one part is I want to introduce our own method to predict sea ice based on melt ponds. And then I will have a relatively detailed look over the last 6 years, what happened to the Arctic sea ice, how were the predictions, and what were some special events in the Arctic. So let's start with the overview. The best quantity we can observe is the sea ice extent, which is the area which has at least 15% of sea ice, which we have relatively good satellite observations from 79 to today. And we see here on the top plot, we see the March sea ice extent, the winter sea ice extent, and on the bottom the September. There are uncertainties because you see red and blue curves, which are two different satellite products. So you see them distinct differences. In particular, in summer, these differences can be up to one million square kilometer. But actually, the variability and the trend is not affected. So we can see actually there is a significant decrease in winter and in summer, and the summer decrease is a bit stronger. If we put that into a longer time series, of course there's much more uncertainty in the data, but we can get from proxy data the best sea ice information about August. And if you look at the August sea ice extent based on some from a paleo time series, which is smoothed here over 40 years, we can see that the current decrease is unprecedented. There were some other periods in the around 1500 and 600 where we had some decreases, but nothing like we have seen in the last 40 years.
How did they measure that? You know how they worked that out? Like what method they used for this?
This is where quite a lot of different data, different proxy data used for that. So this is in this here. You can find some more details about it. And there's a big uncertainty. Of course, the uncertainty is a bit shown here in this, what they assume as the uncertainty of this data. We know that the ice becomes thinner, so this is some combined observations from submarine data and from satellite data for the latest years. There's even more uncertainty regarding the ice thickness, but the result is nevertheless that the ice is becoming thinner, and we have a reduction of multi-year ice, so ice which survives several years. So while we had in 83 up to 20 to 30% of ice which was more than 4-year-olds, so which has this has been reduced to something like 5–10%. So from the observations, it is clear for the Arctic sea ice is in decline. But the decline, what are the reasons for the decline? We don't know from observations alone. So we need climate models to be able to separate what is the impact of natural variability on different kind of timescales and what is actually the impact of climate change. And with climate change, I mean the increase of CO2 due to humans. And this is not so easy to distinguish, but and of course it depends a bit on how accurate the model are. But I think at present, so this is but around 50% of this decrease, they can actually be caused. It's possible that they are caused by natural variability. But on the other hand, it means that 50% of the observed increase must be due to climate change. But of course, how reliable the numbers are depends how accurate the key processes in the climate models are represented. And of course, there's quite a strong physical simple argument. If you increase the CO2, you increase the long wave radiation, and you can calculate the impact, and you get an increase of melt. So it does make sense that the climate change actually, the increase of CO2 affects a reduction in sea ice. So the Arctic sea ice is responding very quickly, and so that's why it's probably one of the most prominent indicators of climate change. But now let's look more actually not on the climate trend, but on more what happens from year to year when we want to make predictions. When we have, for example, a model system, a prediction model system, and this we have forecast errors, there are different kind of sources of these forecast errors. It is possible that in the prediction model we use, we have important physical processes which are missing. It is also possible that we don't know the initial state correctly, which can have an impact. And of course, there is the chaotic behavior of the atmosphere on timescales of more than 10 days. One way to address whether there is at least some potential to make predictions is so-called a perfect model study, where we actually use a model simulation as our observation, and when we from hindcast actually to test, can we predict the model world. And from this study here you can see a so-called correlation skill for Arctic sea ice extent for different months. So this is the predicted month. For example, when we want to predict the September, and we start here with let's say one month ahead, we have quite a high skill to predict the September in the model world when we start when we are in August. And all the dots here, so the colors present the correlation skill, and the dots mark where we can make skillful predictions. So we see for the September it is possible in the model world to make predictions up to 4 months ahead. You can see from this plot that it depends a bit on the time when you make predictions, and for example, there's in February we can actually make not a very high skill, but still a significant prediction a year ahead to February. There are also some kind of barriers where you see where certain periods are. So if you want to, it is possible from after June to make a prediction towards September, but if you want to make predictions beforehand, it's actually not possible.
David,
yeah.
What's the dots where you have correlation skill and you're showing the map of correlations? So what's the criteria for it being a skillful prediction? Is it a particular value of the correlation?
It's a significant test.
It's a significance
yeah.
test. Okay.
I haven't looked.
So it's not a particular value of the correlation, it's a significance test.
I think on this case the significance is actually relates to a value of 0.2 or so. Okay. I don't know the specific case if the test was performed.
The dots are in every yellow part above 0.2.
That's what it looks like. That's why I asked.
Yeah. I think normally this, yeah. This is another study where I actually show what is the also here you show we show the root mean square error for the sea ice extent prediction, and from a hindcast simulations, and for example the black ones is when you start in January and you predict for January and then the following months, and as the dots show we still have a significant prediction. It shows an impact whether you start in January, May or July. So for example in July if you start in July it's only prediction which is significant up to three months. When you start in January, there are actually also some predictions, not for the whole period but intermittently for some winter periods in following years. This probably relates a bit to do with what is happening in winter and in summer. So therefore for winter extent there are some anomalies with ocean temperatures which are longer lasting, and when you start with them you can actually get some skill from that. since 2008, where is the sea ice prediction network organized, where everybody can put up predictions for the September sea ice extent. And there are three time periods where you can put up your predictions. So by the beginning of June, based on May data, at the beginning of July, at the beginning of August, so 3 to 4 months up to 1 to 2 months ahead. And there are different methods applied. So you can, in principle, there are bits which are dynamical when you apply a model to do with your calculations, but there are also quite a lot of statistical approaches where you correlate some quantities with the September DIS extent and make a linear regression and predict that. Some mixed stuff, also some heuristic stuff where you can just make up a number from some kind of information. And these data are now available over the last 10 years. Why can we actually make sea ice prediction? So there are certain quantities which might have an impact on future sea ice. So quite obvious is where you can look at ice concentration and ice extent, the type of ice, temperatures in the ocean, which have a longer impact on the melt onset, the melt point fraction. And then the types normally are the linear regression type. You look at correlations with the September ice extent, and then you can use that and make forecasts for following years. Another possibility is from the model approaches where you use certain initial conditions and you prescribe initial conditions. Based on these initial conditions, can you make some predictions? There are quite a lot of limitations. For example, when you look here, I showed this figure before, the variability of the March ice extent and the September ice extent, you can actually see that they both have a linear decreasing trend, but they are totally uncorrelated. So the variability in March has nothing to do with the ice extent variability in September. So if you want to make a prediction based on the sea ice extent in March, it is not a good predictor. It's not a skillful predictor for the September ice extent, for example. I show here one study where the aim was, and at this work about 10 years ago, to find out what can we where can we use sea ice anomalies for predictions. And in the model, the most strongest impact is to remove all the sea ice from the model and then to run the model and to see what's happening, what is the impact on the following years. And if you do that in December, you get a recovery of the sea ice area within 3 months. So the model is a fully free model with no forcing data. So there's immediately response. If you remove all the sea ice in December, you get a lot of ice growth and your ice extent is back to the climate state. So in orange, this is from the control run, and this is the variability within the model. In this case, it's the HM3 model simulation. If you remove your ice at different times, this looks a bit different. If you remove all the ice in March, when actually you get a bit of ice growth in March, but of course when the summer comes, and then you get a bit of a stronger impact because the ocean can heat up a bit, but still after a bit more than 1 year, the ice extent is back to its original value. And if you look at the volume, for the volume it takes maybe a tiny bit longer to recover, especially if you do it in June, it takes maybe up to 3 years, but you still get a full recovery. So which shows a bit that sea ice anomalies, if the model is correct in doing that, is actually maybe not the best parameter. You could argue, okay, if you just remove the sea ice from a thermodynamical point of view, there's not lots of energy in the sea ice, it's thin. So the next step was to actually adjust the ocean, the next 200 meters of ocean, to a state where we would have no sea ice. If your ocean is changed as well, the impact lasts a bit longer, but after 3-4 years, you get the same result. The model comes back to its original state. And but it's also true if you do the other way around. If you put sea ice everywhere over the atmosphere or double the sea ice, it only has an impact on relatively short time periods. Afterwards, the sea ice state is bound to the climate system in the model, and this recovers. And there was another study which is not only true for the present day, this is the same in any future state. If you remove all the sea ice, the model goes back to its states where it should be till the summer sea ice vanishes. It shows the September sea ice extent. And in here with different ways. There is one reason for that. There is a very important positive winter feedback mechanism. This figure shows here, this is from our own standalone simulation, just the result. It shows the mean ice growth, centimeters per day, depending on the mean ice thickness. And this makes actually clear how recovery works. So if you have an ice thickness of 20 centimeters, you get an ice growth of 10 centimeters per day. But if your ice thickness is a meter, you only get 1.5, 1.8 centimeters per day. And so when you remove all the ice, you get a lot of ice growth. So actually, when you start with 2 meters of ice, you have hardly any ice growth. So at the end of the winter, you come more or less to the same state, independent of what happened before. This is, well, you get some small differences, but they are quite, the impact of the ice thickness at the end is quite small. Saying that, this of course depends on some assumptions on the sea ice model. So it would even be much stronger if you just have one ice thickness category, because then the impact would even be stronger. But in reality, you have always within a grid cell, or you have subgrid scale ice thickness changes. So you have lead formations, and then you have very thin ice. And actually in winter, while we get actually value here of 1 centimeter per day, if you have ice this is 4 meters thick, you wouldn't get 1 centimeter per day ice growth. It would be really close to 0. But you have 1 or 2% of thinner ice in there when the ice growth takes place. So of course there is a bit of dependence how this is accounted for in the model system. But it shows this is the most dominant feedback, most dominant mechanism for sea ice is this positive winter feedback. Which is also shows this has another model simulation where we actually look at the sea ice growth between November and April in this red area from the model design. This is a model which was a bit tuned with cryostat thickness data to produce quite a realistic cycle of ice thickness. And we see that we actually got the largest amount of winter ice growth in 2007, 2008, in 2012, 2013. So after we had the very low ice in summer, we got most of the ice growth. And if we look at correlations, how much is this correlated with the mean temperature over this region, or with the November ice thickness? We see that the stronger correlation is with the November ice thickness. So the thinner the ice, the more ice we grow. The correlation coefficient is minus 0.82. Whereas the impact of the temperatures in winter on the ice growth is relatively small. There is a significant correlation, but with 0.49 it is quite limited. Well, this is a bit a study from Dirk Notz and Julian Ströbe, which actually shows that the winter, is based on that the winter feedback mechanism is dominating, so that we can actually reduce the change in ice area, or that we have the change in ice area is quite linear with the increase of CO2. This is a way that the rate is quite different in the observation and quite a lot of models, but when the models are normalized, which is quite a strong relationship. Okay. Now I want to talk about meltbonds. Generally in CMAP5 models, meltbonds are not simulated. Meltbonds is water when the snow starts melting on the ice, and there's lakes which form on top of the sea ice. In models, all the meltwater is immediately released to the ocean, from snow, from ice, from rain. But they do something with the model. They change the albedo. And there is an indirect accounting for melt points by adjusting the albedo. So we have for the snow the near infrared range and the visibility range for temperatures below -1 degree with our values 0.78 and 0.98 for snow, and for the ice 0.36 and 0.7. When the temperatures are, the surface temperatures is above -1 and approaching 0, the albedo is increased. For snow, which is weird because the snow changes its behavior, so we have an increase. There's a linear assumption for 0 degree is 0.7 and 0.88, and then there's a linear approximation for it between. For the ice, which is quite, this increase is not in a very real. So this is just, and this is an indirect accounting for melt points. So if you have temperatures that become close to 0, we know from observations that the albedo has smaller values to absorb more radiation, so which is just based on the temperature, which was done in most of the models within the pipe model. Okay, a bit more, one step further is a kind of semi-empirical model where we actually look at the meltwater volume and then derive the point fraction and the point depth and calculate the change of that based on the surface temperature. And now I want to talk about the more complex melt point model, which, well, Daniela Flocke has spent most of the work on that, but in a way with Danny Feldheim's group was work over the last 15 years, something like that, on this melt point model. So the principal idea is what the meltwater collects at the lowest part from the sea ice topography. We don't have a topography in the sea ice model, so this is now the version which can be used in global climate models. We just have a relatively simple ice thickness distribution. And so we need to make an assumption, and that is that the meltwater is transported laterally to the lowest surface within one time step in the model grid point, which is not realistic because we have a model grid point of 40 kilometers. It wouldn't be transported 40 kilometers. But the area we actually get by assuming that is quite realistic, so which allows us to do that. And then we look at the amount of meltwater if the lowest category is filled, when meltwater comes into the next category. And snow can here be saturated, is accounted for. So it's just some simple features. Collects on the lowest level. The hydrostatic balance is maintained. Vertical drainage is called accounted for with Darcy's law with a variable permeability. When we have ridging processes, meltwater is lost in the leads, and we transport melt points as a tracer in each ice thickness category in the model. And when we have freezing conditions, a lid can form and this can grow and melt. Okay, I want to show a bit of results with our test in a bit. First, in a simple standalone sea ice model. For the Arctic, which is the model domain, we use atmospheric reanalysis data for the forcing. We have a simple mixed layer ocean model with a fixed depth and prescribe the salinity of climatological monthly means. And the temperature, the ocean temperature, is prognostic, but we use a restoring term because otherwise it's just one-dimensional and we need to account for advection. So we do this by the restoring stuff, so which is our general setup. And then we can run the simulation. This is with NSEP forcing data, and we see here from the Hades sea ice concentration. Here's the Hades sea ice concentration for September, the climatology from 1979 to 2012, which is our size product. The extent is okay, we get a bit lower ice concentration here, but in a way this is not too bad. And if you compare here the ice thickness with the biomass ice thickness in March, which is what our model is doing, so it is quite reasonable what the model is doing. But now we look at actually the melt points, and I show here an example, which is this is for 2012. It starts in 20th of May, this is day 140 to the mid of August. On the left, we see the melt point fraction. On the right, we see the melt point depth. And it starts now. So we can see the first melt points form the end of May. The blue is fractions under 10%. And then by the end of June, we get 30, 40, up to 60, 70%. And when in by beginning of August, lids forms, and when the meltpoints are not counted here anymore. We still have a death here because, of course, when the meltpoints can be trapped, they're not open, active from the albedo point of view. So there is quite a lot of interannual variability. And we look a bit more in general how they look like. So we see the meltpoints form in May, and they are covered by a lid by mid-August, and we see strong variability. So if you look at the mean from 79 to 2012, which is this black line, so we have hardly any meltpoints till the end of May. We have a maximum about 20% in July, and when they are vanished here. But we see strong interannual variability. So if you look at the periods in the 80s, we are here, and if you look at the 2000 to 2012, we are here. And most striking, if you look at extreme years, for example, 2012, the year with the minimum September ice extent, we see we have the largest amount of meltpoint fraction in this year. And if you look at 96, this was the year where we had the lowest ice, we had the maximum ice extent in summer, we have the lowest meltpoint fraction, which motivated us to look how much which is correlated. And we found out that we actually get a very strong correlation for detrended values. So of course, we have both have a trend, the meltpoints have a trend, and the September ice extent has a trend. So you have to detrend it, of course, to test this how significant that is. And we have a quite high correlation value for the anomaly of the pond fraction, and in early in the season, so in May, with the anomaly of September ice extent. So we can use that actually to make predictions on a very simple linear model. So we look at the amount of ponds we have in May and June, and we can use that for predicting the September ice extent. I should say we don't use there's still a skill if you just use the average pond fraction for the Arctic, but the skill is better if we look at regions and do pick out regions which have stronger correlated, and when we get a higher correlation, as I said, can use it as a better predictor. It is always difficult. I distinguish here between hindcast and forecast. So if you look at correlation, and when you do the hindcast using this, of course you get very good results. But of course, there's always a difference when you want to make a real prediction and you don't have any information what happened in the past. So it's always quite important to distinguish how you do proper forecast or without using any information. So if you make a prediction for 2012 for the lowest value, it makes a difference that we had already values till from 2012 or afterwards or not. So to make a fair prediction, you're only allowed to use information from beforehand. The reason why we get the meltpoints as a good predictor is there is this positive feedback mechanism, which is with the albedo mechanism, but is in particular with ponds, even stronger than for open water, because the open water fractions are quite low. So then you have more meltpoints than usual. You reduce the albedo heavily, so you get much more absorb much more shortwave radiation. So if the ponds increase, you get more melting, and this results in the lower ice extent. And this also accounts our system for a bit of preconditioning, because if you have very first-year ice, which is quite flat and homogeneous, then the ponds immediately cover a larger area, so the effect is much stronger, so you get more melting. If you have rougher multi-year ice, where you have we have small parts which are lower than the thicker ice, so the same amount of meltwater covers only a small area. That means the impact is much weaker. So it counts for both, and that's I think the reason why I think this is a good predictor. Okay, now I want to go a bit through the years, the last seven years. This information that I show here, quite a lot comes from the Arctic sea ice block, from Neven. This is quite a nice information about what's going on, and from the NSIDC page, the monthly Arctic sea ice news and analysis. So if we start with 2012, so this is the September ice extent till 2011, and now we have 2012 is the lowest year. The real value was 3.6. So if you look at the in July what the different group were expecting for 2012. All of them expected a higher value, and significantly higher as the mean of them is about 1 million per square meters higher. So if you look a bit on the time series of the ice extent, so we see here in green, the green is 2012. So if we are here in, for example, in June, we see here 2010 as a reference, which is actually what most people predicted. So if you make a prediction here, we see that we actually are online with, from the sea ice extent in June or so was the same as in 2010 as in 2012. So understandable that some predictions might actually expect the same. So what did happen here later? So let's see whether I can. So this shows an animation of what happened in August 2012. So the colors is the wind. So we see here a wind speed up to 14 meters per second, and it shows the period from the 1st of August to the beginning of September. So white here is the sea ice, so we should look at the beginning, what's happening to the sea ice, because this is something very special. This has that way never happened before in the satellite period, also not really afterwards. So look at the beginning. You want to restart it? Sorry. Oops. Okay. So let's start on the first. We have quite a normal sea ice extent, and then we see here a strong storm coming in, and a huge area of sea ice vanishing within a couple of days. And this is there is some theory that also waves might have here contributed to this kind of strong decrease. This cannot just be drifting the sea ice. No? So even when the wind is quite strong and the ice drift is strong, just the drift would not explain the huge amount. I might start it once more.
Well, what is the theory? Has anyone said why are waves involved in that or not? No one's quantified it. Nobody said how much of a role waves played in that.
I think
Yeah.
not many people are focused on that. I think the majority of people think that ocean heat is causing the melt. So they're just mixing up the ocean heat.
Through that onshore wind.
Yeah.
Yeah.
I think that effect is probably at least an order of magnitude bigger than waves.
I mean, it's definitely an interesting case to study. What is when you have a wave model implemented to study this month, what could potentially be the impact of wave and wave breaking. But of course, the ice was quite thin and vulnerable before it, so there are lots of possibilities. It doesn't have to be the waves, but it could have played a role in
That's the range of wind speeds.
which is the range of wind speed, yeah, according to the colors. So it was one of the strongest, or maybe to that date, the strongest summer storm which has ever been seen in the Arctic in the last 40 years.
Do we know anything about the sea speed, ocean speed?
We can. I can't show it here, but I mean the ice responds quite quickly. So we get probably ice drifts here up to 30, 35 centimeters per second, and then the ocean currents under the ice follow as well. Yeah.
So that's pretty fast for the Arctic.
So why is the model failing? Because it's got the thermodynamics correct, but it doesn't know that the wind's going to blow like that.
Well, this is a model failing. You are talking about predictions.
Yeah,
But if you make a prediction, of course, in July, we don't know what the storm will be there, because the atmospheric behavior is chaotic. So we could maybe say there's a more likelihood for something like that, but we don't know what this is happening. So from a prediction point of view, you cannot predict such kind of event. Okay. So we can. This is shows a bit the temperature. A ranking for the 925 hectopascal temperature, so the temperature at, what is it, about 700 meters above the ground. This is a bit better than the surface temperature because it does not really directly reflect just the ice ocean edge. And this is a ranking. So blue means cold, and red means one of the warmest within the last 40 years. So if you look, for example, and this is from January till December. So if you look here in 2012, we see we had the third warmest January, February, the March was actually only 14th, and when we had in 2012 a very warm spring, early summer period. We were among the warmest and later and where as well. So we had throughout the whole year, it was quite a warm year, but particular here. Which also, as the spring.
That's a bad way to plot that data because it's so.
Say it again?
That's a very bad way to plot data because the difference between the 23rd and the 24th could be almost nothing. You know, those numbers are meaningless, right? Like.
The different, yeah, but I mean, it just shows, the color just shows whether it was quite warm or it was quite cold, which is not.
I think that's a terrible way to visualize data.
Okay, your
You're
opinion?
just putting it out there because you've got no sense about what the difference between 20 and 23 is. It's not the same as between 3 and 6. I almost guarantee that. You know,
But the temperature distribution for a certain month can be a bit different from month to month. In summer you have a narrower distribution, so the differences are smaller. In winter you can have differences between the warmest and the coldest. Winter is about 12 Kelvin as the average mean temperature.
one sentence, the numbers mean nothing on that plot.
The numbers may mean nothing, but the colour scale.
Yeah, so get rid of the numbers, yeah.
If I would show you, I don't know, the point I showed with, I understand what you say. If you want precise stuff, it doesn't help, but I don't want to show too many details, so I just want to give an impression at what time of a year in the last year it was warm, and I think this shows that a bit that 2012 was pretty warm. Whether it's 4th or 3 or 6 or whatever,
Yeah,
no, there's quite a lot of red throughout the whole year, in particular here in the spring period, which is the point I want to make. Yeah, sorry.
Okay. Just to make it more awkward. So 2007 is quite a warm year as well, isn't it? And that was another year.
Yeah, we see 2007 was the year when we had the extreme warm summer here. The record temperatures for the summer are still hold by 2007.
Yeah, 2016 was the warmest, and that wasn't the year of OCS.
Yeah, I will show this plot 6 more times.
We're all friends here, right?
Make you happy. Anyway, in 2012 we got a lot of melt points. This shows the melt point anomaly in our model, and we, this is for June. We had a very low ice volume, so the Palmer's data, of course, there are some problems with this data because it's just a reanalysis product which assimilates ice concentration but not ice thickness. But 2012 was low and we had a lot of melt points. So there were some indicators what it was possible to predict that. So it was a warm year, we had a sunny and warm spring. We had the August storm, which is not possible to predict. Okay, let's come to 2013. 2013 we did see a strong recovery, much higher value than 2012. The predictions didn't expect that. So if you look at the predictions, well, actually, let's to be fair, they predicted the values a bit higher than 2012, but much too low from the real stuff here. This is the June report. So if you look at 2013, we do actually have here, when we make the prediction, the ice extent at this time is was quite similar to 2012, but it ended up then much higher. So what's happening? We see here on this plot, the temperatures were different than in 2012. So we had one of the coldest February, but that's probably not so important, but it did lead to more ice growth, so the ice volume did already increase in the winter, and that one we had quite average temperatures for the whole period, pretty cold for this kind. So in particular in spring we had the melt formation in May was very low, and we got an increase in ice volume. It was a recovery, so we were at the lowest value at the beginning of January, but now we are not at the lowest. So that ended up in a higher value. In 2014 it stayed a bit on the higher value. Predictions were a bit better, but still underestimating it a bit. We did have a bit lower ice extent beforehand, but it's not. And if you look at 2014, we had a very warm winter. So, but due to the negative feedback mechanism, the winter ice growth does not depend so strongly on the temperature, so which did reduce the ice volume a tiny bit. But when we had a cold spring, which did lead to another recovery here, so we get an increase in ice volume 2013, 2014. You can see here low melt points again. And in 2015 it did go up a bit, but not that much as you might expect. When we looked in the winter 2015, we had the lowest ice extent ever, but significantly lower than ever before in winter. And nevertheless, the 2015, it did not end up as low as expected. But actually, the predictions were relatively realistic in general there. Impact there for the winter stuff is quite related to SST anomalies. So we had a strong positive temperature SST anomaly here in the North Atlantic, which did cause a reduced winter ice extent and had impact at least on the coastal regions here. So if you look at 2015, was in a way a bit mixed, but it had here in spring, in May, it was still quite cold, so the ponding was quite weak. In 2016, it stayed pretty much on the climate trend. In 2016, the winter extent was even lower, and we had in 2000, so the prediction underestimated 2016. The SST anomaly was stronger and also a bit here from the Pacific side, and when we had the warmest winter ever, so the mean anomalies for the air temperature were about 6-7 kelvins above the average. So we were about 4 Kelvin warmer. About 7 Kelvin warmer than the year before, and about still 3 Kelvins warmer than this year. So it was an extreme mild winter. The spring was not that cold. It was also relatively warm, but it was quite cloudy. We had quite low pressure, so we still didn't get lots of melt points. So the melt momentum was weak. I show here some surface pressure. So this is a high pressure we had in 2012. That means this was very sunny in 2012. In beginning of June, which is the time where the pond formation takes place. Whereas in 2016, the temperature was also quite mild, but we had a low pressure, and it was quite cloudy, mild and cloudy, and much less sunshine, so the melt formation was weaker. And we see in 2016, when in August, but the end of August, also quite similar to, go to the next plot, continues here, end of August, beginning of September, quite similar, a large area of ice fraction vanishing due to an impact on a cyclone as in 2012, but it was 3 weeks later, so the impact was quite weak, and in that on the daily minimum was quite low, but it actually, as soon as the wind stopped, it did go back immediately, because it was so late in the year that the ocean temperature was at freezing temperature, and when it did go back. It happened a month earlier, a cyclone like that, where the stuff is moved when the ocean can warm up a bit still, and when it is a longer impact. 2017, nothing spectacular, but again, very low winter extent. The predictions were actually a bit underestimating, 0.5 towards the anomaly is weakening a bit, but still there. And if you looked here, we had 2016 was an extreme warm year, but we had an extreme warm autumn. So the ice growth started quite late. So we had the lowest ice volume, at least according to biomass here. But when the temperatures were not that high in the May-June, so the melt formation was slow. We had also a bit more snow, which wasn't, the warmer winter meant a bit more snow. We had a very cold summer as well, and so it stayed quite low. If we look how skillful are these predictions, we see actually here that in years where the observed value is quite close to the climatology, the predictions are not that bad, but the extremes, yes, are not predicted, at least not by the mean value from all the contributions towards that. So in a way, from the prediction, the mean from the sea ice outlook is not really better than a simple trend prediction. Also even for the shortest period, there is no skill. If you look at individual predictions, so some of them seem to have, the time periods are relatively short to make a fair assessment. But if you look, for example, which kind of prediction was the best over the last 5 years, and you look at the short term, so the prediction just 1 to 2 months beforehand, there is a method from Andrew Slaughter. He had actually this other observation values, and this was his error. This is comparison, the error, prediction error from the mean SAPI. So he was a very skillful prediction, and which is based on a 50-day lead time forecast of Arctic sea ice extent with a model simulation, which actually counts for probability and uses this as a prediction for the whole extent. And if you look at the longest period, the 3 to 4 months, you can see that actually the meltdown prediction performed best. So the errors here from the meltdown predictions were very low. This has to be, I mean, they are lower than they are actually on the long term from our calculations, because all these five years were actually years with a kind of recovery, where actually the spring was relatively cold and cloudy, so the melt formation was weak. But it demonstrates the impact of that. I want to say where are actually, surprisingly, from sea ice concentration, you can get better predictions, even though the sea ice extent is not correlated from sea ice extent in April towards the summer. But if you actually look at the right locations, there are locations, of course not the locations around the ice edge are not, don't give a good skill because it depends just on the SST anomalies, but in some areas you can get more skill. And if you actually use melt onset, it is possible to make some significant skillful prediction from March onwards. Okay, some messages. I think this is important. Sea ice anomalies provide limited skill for predictions because sea ice changes very quickly to the climate state. So this is quite difficult to make predictions from that for longer periods. When we look at temperature anomalies in the ocean, this is possible. They sometimes last for a couple of years, so there are skillful predictions possible, mainly for the winter sea ice for up to 2 to 3 years. For the summer period, it's clear that the albedo feedback is the best source of prediction. This makes this possible. And I think what we learn in general for global climate models, we need accurate representation of the negative winter growth feedback and the positive albedo summer feedback. The negative winter growth feedback is the main feedback that actually is responsible that they still have sea ice, and this is at least quite dominant as long as we have winter sea ice. If we come to the state where, for the summer sea ice, when it vanishes, it will always recover. When we come to the state where actually the sea ice melts very early in the season, this winter feedback will be weakened, because then actually the ocean temperature can heat up and there's a stronger response. And for the summer, of course, it's the albedo feedback related to melt points and leads, which has to be accurate in models to be able to provide projections for the future accurately. Thank you.
Questions? Well, I'm told for pretty much all of this.
The negative winter growth feedback is just simply the fact that if there's no ice, it grows rapidly and then it slows down, right? Is that?
This is well, yeah. And if the ice is thin, the ice is thinner than the year before, it goes faster. So at the end of it doesn't actually matter where you start from. At the end of the winter, it's exaggerated. The ice thickness is the same.
So the conductive heat flux through the ice roughly proportional to the temperature difference divided by the thickness of the ice. So it's inversely proportional thickness, so thin ice goes faster.
I don't understand you've got all these people making these predictions which seem to follow the same distribution almost every time. Like most of them are in this band and there's a few outliers. Is that, like they seem to have a sort of curve on the predictions, right?
Mm-hmm.
Now, is that the fact that, is it every year that these guys are always too high and these guys are always too low?
Not necessarily.
Like that sort of seem to have the same.
There are some other this is quite, I mean, there's some a bit random, sorry, some random methods as well. So there's quite a big variety of kind of predictions. So
But they're not consistently too small, consistently too large.
Well, one prominent one has been removed from that to a consistently small. Apart from that, I think it's pretty much all over the place.
Yeah, from year to year.
Yeah.
it's probably that some prediction may lead to have a small bias towards positive and some to negative. This is possible as well. You have to look at the details of this.
So what's driving that variability? There's different, I mean, they've got basically the same, the models are all basically the same? Or?
Well, they're not all using models.
Oh, some of them are the same.
No,
Yeah, yeah.
so
No,
about a third of models, a third of statistics, a third of tea leaves.
Tea leaves doing this.
Well, actually, just drawing a line through the
There's a
trend,
list of
extending it.
different ways of predicting you showed somewhere.
Yeah, it was color coded.
Which does better than statistical or?
well, if you look at the average, they are all like more or less all the same.
Julian
Um,
Schroeder wrote a paper basically saying there was no systematic improvement of the models of statistical techniques.
Yeah.
Or vice versa.
But
Were the best two that you pointed out at the end both models?
statistical. If you look at individual ones, I did the statistical seems the best. If you look at the individual predictions, how they perform, I think the best 3-4 are statistical. Of course, this is a bit simpler to perform that. When in a model you have lots of error sources, which might be a bit more problematic. And if you can just focus on this positive feedback mechanism in a statistical method, simpler. But we have to say also in the models there might be even important stuff missing. Like for example, the melt points that we have shown is quite important. They are not properly accounted for. So
Yeah,
just some
also,
weaknesses.
for example, the prediction scheme that we've been producing, the CPOM one, it's marked as statistical, but actually it's more hybrid because the model predicts the spring melt point fraction, but then with that statistically correlated to this at 10%, so it's a mixture of the two.
So why isn't it down as mixed there? Some technical reason.
This is just how they decided to color code it.
Click the box yourself and you provide a prediction.
But how, so when you're making this prediction, how far in advance are you making it?
Yeah, there are 3 different periods. You make one in beginning of June, so you put principal data till the end of May, which is the first one. So it's 3.5 months before we have the minimum in mid-September, and then 1 month later in July and August. So
Okay.
which are the 3 periods? Yeah.
You're predicting 1 month, 3 months ahead, 2 months ahead, and 1 month ahead.
So what David didn't mention, he mentioned at the beginning there was a very weak correlation between winter sea ice thickness and summer sea ice extent. Okay. But in recent years that's been all over the media because Cryosat started been measuring sea ice thickness in winter in the Arctic for the last 5 or 6 years. So we've had several years of very record low sea ice thicknesses in winter. And of course the media is all saying, well, that means the ice is going to be doomed come summer. But actually what this is showing is that ain't the case. Negative feedback mechanisms dominate, and so no matter how thin it is in winter, at least at the moment, it's recovering enough.
So earlier on in the talk you showed that February was always very predictable. Is that because February is kind of always the same, or is there some other reason?
Well, this was from a model study, so I don't know what's the variability in the model for February in this case, but I would say from in winter period it depends quite a lot on the ocean temperature anomalies. So this is when the ocean is a couple of degrees warmer, the ice extent cannot go further, and they have a cycle. They last 12 months, so even longer. So then you can from 1 month to the other. But it's better in February or in March, I think, which is probably random or might be just a model issue.
Well, there is an argument about the predictability barrier, so that when spring kicks in, you start to have positive feedbacks like the albedo feedback, causing amplitude of any discrepancies from 1 year to the next, which is why predictability drops after then. February is like the end of winter, okay, and well, it's pretty cold in winter. It always is cold in winter, okay. And February, you're after the winter period, so you're integrating the uncertainty and variability over the winter period. So that may help to explain why you've got greater predictability in February. Okay.
The melt pond model looked like you need the topography of the sea ice.
That's right, yeah.
I don't think you have that in size.
Not,
How do you,
we have an ice thickness distribution. We have 5 different ice thickness
but that's different from
categories.
the topography.
It is different than topography. Yeah. There is a kind of we assume that the whole stuff is in equilibrium, but when we can actually calculate what is the sea level, and when we calculate the bits which are over, and when we can look what's the difference between the free water between the ice thickness classes, and when we use that as a proxy for topography.
So this is a fundamental limitation of models, right? They don't have topography in. So no matter how much you wish for it, it's not there.
Sure.
So you have to make some assumptions, right? So the original model, the 2007 model, was not a client model, so you couldn't track topography. That was fine. In the client model, you have the thickness distribution. So we simply make the assumption that on average, the ice in each thickness class is in hydrostatic equilibrium. Okay, on average, that's the case. And if that is true on average, then the thinnest ice on average is also the lowest ice.
Right.
Okay, so in which case it makes sense to pump the water there than on the thickness ice. Okay.
You showed a video of atmospheric storms during summer, I think it was.
Yeah, August 2012. Yeah.
2012, yeah. And clearly the ice shrank back with the storm, is that right? The ice-
Yes, it happened at the same time. This is right.
Yeah.
That's what is the case. What is the reason and what is the consequences? Where is a bit discussable, of course. Always is a bit
Okay.
opened. So of course, when you normally have a storm, the ice is pushed back. That always happens. But the speed, the ice vanished in August 2012 was too fast, so it wasn't just drifting away. It melted. Also, whether it was just because it was so thin and melted under normal, like the sea ice model would have calculated as well, or it needed it needed waves to flood the ice to increase the melting, or did put it in smaller ice flows so that the lateral melt was increased. All this probably comes together to actually achieve what happened here in August 2012. This is not proven in a way, but
No.
But you said that the predictions were wrong because of the storm, but were the hindcasts successful for the August 2012 or?
I don't know actually how accurate. Also, if you look, of course, it's just for September extent where you can hindcast are okay, but so from that respect, yes. But whether actually hindcasts are possible to have the development in August, correct? I haven't seen any who reproduced this 10 days of event to do so. But to this extent, I don't
So
know.
even if you have the wind data and everything, it's still not very possible with the current models to.
I haven't seen any model to perform that. I wouldn't say it is not possible. It might be that some model performed that, but
Maybe that's not entirely true, isn't it? Because haven't you done it?
I haven't looked at daily data.
Oh, not daily
stuff.
data,
So
no.
which is, I mean, we
But
can
true.
perform the September extent correctly, but the speed in which this happened, we cannot reproduce in our model.
Oh.
Let's think of it again.